Welcome to The Explainer. Today, we're jumping right into this high-stakes race for true quantum advantage. And it makes us ask a pretty provocative question.
So what does that even mean, truly quantum? Well, it's not just about faster. I mean, that's part of it, sure. But the real deal is solving problems that are, well, they're fundamentally impossible for even the biggest, baddest supercomputers we have today. We're talking about problems where a normal computer would literally need longer than the age of the universe to spit out an answer. No joke.
This kind of mind-blowing speed-up has a name: exponential quantum advantage, or EQA for short. And let me tell you, finding a real-world problem that actually has it, that's pretty much the holy grail of quantum computing right now. It's what everyone is chasing.
Okay, so for a long time, everybody thought the most promising place to find this advantage was going to be in quantum chemistry. And it was all based on this one really simple but kind of profound idea.
The idea goes all the way back to the legendary physicist Richard Feynman. And the logic is just, it's beautiful. He basically said, look, nature is quantum mechanical, right? Molecules, atoms, all that stuff. So if you want to simulate nature, you'd better use a quantum computer. It's like speaking the same language. It just makes sense.
So what's the actual task? Well, for a ton of chemistry problems, the central thing you need to do is find a molecule's ground state energy. All that means is its lowest possible energy state, its most stable form. If you can figure that out, man, you can predict all sorts of things about how it'll behave. We're talking about everything from designing new drugs to building way better batteries. It's a huge deal.
But, and there's always a but, isn't there? As scientists dug deeper, this really promising path started hitting some unexpected roadblocks. Turns out, simulating nature, even with the right language, might be a little trickier than we all hoped.
And yeah, the gap between what we expected and what we're finding is pretty stark. A lot of this comes from recent work by a quantum chemist named Garnet Chan. He's suggesting that this whole EQA hypothesis for chemistry, it might not hold up. You see, the assumption was that for a quantum computer, this would be easy, and for a classical computer, it'd be exponentially hard. The reality? It's way more complicated, and in some cases, it's almost the exact opposite.
So where's the hang-up? It's a critical step called state preparation. Think of it like this. To get the right answer, you have to give the quantum computer a really good starting guess. But what Chan's research shows is that as the molecules you're studying get bigger, finding a guess that's even in the right ballpark becomes exponentially harder. It's like this massive upfront cost that basically eats away the quantum speedup you were banking on.
And then there's the other side of the coin. Our good old classical computers, they've turned out to be surprisingly good at this. For a lot of the problems that chemists are actually trying to solve day to day, the best classical algorithms are already scaling polynomially, not exponentially. So they're not hitting that impossible wall we thought they would. They've found some really clever workarounds for these kinds of structured problems.
So all of this leads Garnet Chan to a pretty sober conclusion. He's basically saying, look, quantum computers will almost certainly give us some powerful speedups for chemistry. Polynomial speedups, which, don't get me wrong, is still a massive win. But the evidence for that truly exponential advantage, that holy grail we've been talking about, it's looking pretty weak.
Okay, so if the exponential jackpot isn't hiding in a natural problem like chemistry, then where is it? Where else can we even look? Well, this question leads us down a totally different and honestly fascinating path. So a cryptographer named Mark Zandri came up with this really radical idea. He said, what if we're looking in the wrong place? What if searching for a hard problem in the natural world is just a dead end? What if instead of finding a hard problem, we just build one? Create a totally artificial problem from scratch, one that's specifically designed to be an absolute nightmare for classical computers, but a piece of cake for a quantum one. And his idea is basically a cryptographic trap. Here's how it works. First, you define a big set of possible correct answers. Let's call this a code. Then, you throw in a second set of rules, but these rules come from a completely random function. Think of it as a black box that just spits out random yeses and nos with no pattern, no logic, nothing. The challenge then is to find an answer from your original code that also satisfies all of these totally random, structureless rules.
And here's why it's a trap. A classical computer is completely blind here. There are no patterns, no shortcuts, no structure to exploit. Its only option is to just start guessing, one by one. And that, of course, would take an exponential amount of time. But a quantum computer, it can use superposition to look at the problem in a totally different way. It can create one quantum state that represents all the possible answers in the code and another state that represents all the random rules. And then, using a clever trick with something called a Fourier transform, it can basically just find the single place where those two giant sets overlap. It turns an impossible guessing game into a solvable puzzle.
So where does this leave us? Well, it seems like the scientific community now has two very, very different quests for the ultimate prize in computing. We're talking two completely different philosophies for finding that exponential advantage.
You've got one path, the chemistry path, which is really pragmatic. It's a natural, physical problem that might only give us these powerful but polynomial speedups. And then you have this other path, the cryptographic one. It's theoretical, it's abstract, but it offers a provable, if totally artificial, exponential advantage. It's like one path is trying to understand the universe as it is, while the other is building a new universe just to prove a point.
And this brings us to a really mind-bending possibility. The very first time we see a proven, honest-to-goodness exponential quantum advantage, it might not be for solving some grand mystery of the universe. It might actually be for cracking a puzzle that we designed ourselves for the sole purpose of proving that it could be done. So that leaves us with one final big question. Will the first true quantum leap be found in nature, or will it be built in a lab?